up on. All right, is everyone doing okay with me so far? I will tell you these two chapters are combined because they're so damn easy, and especially chapter 16. There's one kind of tricky little thing you got to make sure you know. They're easy. So I'm telling you, the rest of my content for this semester is easy. It's not that hard, but the final exam, I'll just remind you, is comprehensive. It's every single type of calculation we've done all semester. That's why I want to make sure those of you that struggled on this last test, we got to fix you because I don't want you to go down in flames like that on the final. That would be really bad, all right? So what I can do for that, well, let's do it. But let's move on to a little bit of stuff we have to know. So chapter 16 is about reducing and enlarging formulas. And it's easy, but it's an important thing. I'll just back up. A lot of times in pharmacy, and you know what I've said next semester, you're not done with me, we're going to do compounding. We're going to make actually creams and ointments and everything else, and usually there's a recipe. There's kind of an instruction on how to do it. The problem is where that recipe comes from would call for in a quantity very different than what you want to make, and I know that's no different than cooking. In what we're simulating, it's a community pharmacy. You're making one ointment for one person. You need very small amounts. But think about this. Do they also compound things in the hospital? But don't they have a lot of patients that need the same thing in a hospital? So their quantities, they make much larger batches because they got a lot of patients they want to make this and be able to use to for a month or whatever it is going to be. So their quantities need to be larger compared to a manufacturer that's making ginormous quantities for wholesale distribution. So you're going to be getting recipes for lots of different quantities that you're going to need to adjust for what you need. And I'll say, for example, USPNF, which is basically a recipe book for formulas that have been around for a long time in pharmacy. They tend to standardize all of their recipes for like 1,000 grams or 1,000 milliliters. That's fine, you've got the recipe, but that's not what you need, so how do you adjust it for what you want? The key thing is here, it's a very one-step process, but you must keep the proportions. Even though you're doing a different total amount, the relative proportions of this ingredient to that ingredient to that ingredient have to be maintained. So you have to just adjust everything in the same way or by the same proportion. So we'll show you that, it's not hard. So this question says, how much of each ingredient would be required to prepare 200 15 milliliter bottles of this eardrop? So again, this would be more like a manufacturer. You're going to make a large quantity of these eardrop products. We want 200 bottles, and each bottle is 15 milliliters. The recipe for a single bottle, essentially, well, not a single bottle, but a certain number of bottles, is to use 1 gram of ciprofloxacin with 50 milliliters of propylene glycol to be combined with enough glycerin, don't forget the QSAD, to up to 100 milliliters, okay? So ciprofloxacin, propylene glycol, and whatever amount of glycerin you need up to 100 mils, that's the recipe we have, all right? So where would you start? The first thing you need to start is, okay, I need to know my total batch size. Okay, I've got a recipe for 100 mils, but that may not be the total amount I want to make, or we'd be done with this lecture, so that's not what we want. We want 215 milliliter bottles. So not difficult, take 200 bottles times 15 milliliters per bottle, and what I'm saying is the batch size I need is 3,000 milliliters. And circle the word desired. I wanted to separate terms here. What we desire is 3,000 milliliters, okay? So this is the only little thing you got to know. The next step when you alter, again, a product formulation quantity is to calculate an adjustment factor. So again, the key thing is the adjustment factor you're going to come up with starts with the desired amount divided by the standard amount. Okay? Desired divided by standard. Everyone say desired. Desired divided by standard. That's all you have to do, because in this formulation, what we desire is 3,000 milliliters. What we're going to divide by is the standard amount in the formula. So again, it calls for 100 in the formula. So 3,000 divided by 100 is 30. And remember, and notice that the units cancel. So this is a unitless value in this case. There's one exception I'll show you in the next question, but in generally, the adjustment factor is just a numeric quantity factor to adjust each of your quantities by. And in this case, we want 30 times the amount called for each ingredient in the formula, all right? Easy enough, but remember, desired divided by the standard amount in the formula. Come up with that factor, multiply that factor times everything in the formulation, okay? But be careful and be organized, because I said that the factor itself here doesn't have units, so you've got to be careful with your units. So line up each one of your ingredients and write it carefully, because for the ciprofloxacin, it's 1 what? 1 gram times 30, the adjustment factor, equals what? 30 grams, okay? I know you're thinking, what the hell is he talking about? But it's for propylene glycol, it's 50 what? Milliliters times 30 equals what? 1,500 milliliters. Keep the units consistent. Remember, don't mess up your units. And this is the one that's most important. Let me ask you this. The glycerin said QSAD 100 milliliters, so 100 milliliters times the adjustment factor of 30 is 3,000 milliliters. So does that mean we're going to use 3,000 milliliters of glycerin? No, it doesn't change the what? The QSAD. Remember, we're still only going to add up to a total of 3,000 milliliters, all right? So while you can adjust the numbers, you need to be really careful that you don't mistake the units as you're doing that or change the intent of the prescription. Remember, everything has to be maintained in the same proportion as the original prescription. We just need to change the actual numeric value. So in this case, since we're creating a batch that's 30 times as large, we need 30 times the amount of Cipro, so I need 30 grams. I need 30 times the propylene glycol. I need 1,500 milliliters. And lastly, when everything's mixed up, I'm going to add enough, essentially, glycerin to a total volume of 3,000 milliliters. What would happen if we need a batch smaller? What if we only wanted to make 2 or 1 bottle? Then instead of 100 mils, say I needed 10 mils. Okay? What is 10 divided by 100? 0.1, right? So, no. 10 divided by 100, so, all right, so we have 10%. So 10, your factor would be 10. No, what am I doing? 10 divided by, I'm moving on. So anyways, do the simple math for yourself here. What I was trying to do before I totally botched that up here is that your adjustment factor can be less than 1. All right, are you with me on that? So if you're making the same amount, your adjustment factor is 1. If you're making a smaller amount, adjustment factors can be less than 1. They can be fractions. They will reduce the amount of each ingredient, but it works the same way. And boy, I really messed that up. The only exception, the only way to make this even a little bit different is if I don't give you a specific unit. So in this formulation for a topical, I want 5 pounds using this formula. But again, you guys you like parts now, you understand parts. I give you relative amounts. I need 10 parts of zinc oxide to every 15 parts of gelatin and 40 parts of glycerin and 35 parts of water. See what I'm saying? I give you relative amounts for all of that. How would I adjust that? Because I want 5 pounds. So how would I calculate that? So the first thing I would tell you to do is, let's get rid of pounds. Nobody likes pounds. Let's convert that to metric. So I would convert my 5 pounds to grams by multiplying by the fact that there are 454 grams per pound. So if I do that, then pounds cancel, and clearly my batch, the amount that I want using this formula, is 2,270 grams. Okay? That is my desired quantity. All right? That's the total. Would you agree? The total amount needs to be that. So what is the amount called for in the prescription? Well, I don't know it by weight, but could I tell you what the total number of parts would be? That would be the next thing. Let's just add up all the individual parts. So the total counted for in the recipe is 10 parts plus 15 parts plus 40 parts plus 35 parts. You add all those parts together, and it ends up, and this is maybe just random, but it ends up being 100 parts. And again, that's the total. All right, so those are the amounts. I have a desired amount, and I have a total. And I know my units aren't the same here, and that's why the only real trick that you could possibly happen on these questions is you still put the what over the what? The desired over the standard, and in this case, my desired was 2,270 grams divided by 100 parts. Make sure you realize this, where this stuff is still coming from. That's there. That's there. And now I get the same kind of thing. I get an adjustment factor of 22.7, but did my units cancel? They didn't. So you got to remember, you got to keep the units. So my units now are what? Grams per part. I know I need 22.7 grams per part for the amount, for the batch size that I want to make. Is everyone okay with where that came from? Same thing, but now my units didn't cancel, but that don't matter. I need 22.7 grams per part. Could you now possibly figure out how much of each specific ingredient you need? Absolutely, because you know how many grams per part. Just take each ingredient, take the total number of parts. Again, for zinc oxide, I needed 10 parts. If there are 22.7 grams per part, 10 times 22.7 means I need 227 grams of zinc oxide. I won't read you all of those, but hopefully that makes it pretty straightforward. Again, I don't think these are particularly difficult questions. Now this one you had a couple of things that you have to go through, but once you know the grams per part, it's the same for all of the ingredients. You just take the number of parts times that factor, 22.7 grams per part, and you get the total amount. Any questions on that? And I would tell you, and again, for the sake of the lecture time, I didn't go through a bunch of these because I think they're pretty easy. There was another podcast, not so much the lecture as it is that supplemental kind of example problems that I do for this chapter that has some that are below 1 and some that are above and more worked examples if you want to keep working on this adjusting formulas. But that's kind of all I was going to do unless you guys have some questions or want to review all that. What might be a little more challenging, I think, was the chapter 20. It's still related, and that's why I kept them together, is this idea of being able to go between the weight of an active drug moiety and the weight of its compound, or from the weight of the compound to the weight of the active drug moiety. That is important. You'll see a lot of those issues in pharmacy practice, for real. So let's make sure you understand. So when a doctor wants a drug, you want to have a drug create a therapeutic effect. It's got this pharmacologic effect, right? You're all into pharmacology now, right? Well, that drug itself has to be administered into the body. That drug, what if it's a polar drug? Polar drugs, do they go across biologic fluids very well? Can they be absorbed into the intestine? No. So what do you do if you have a really good therapeutic drug that's polar? You mix it with something. You mix it with a hydrochloride. You make a salt out of it. You make an ester. You make some sort of more complicated molecule. Look at this list down here. So here's all of your drugs, some sample therapeutic agents. See all of these things here, these more complicated structures? Those are all the active agents. That's the only thing you need into the body to produce an effect. So why is it mixed with succinates and sulfates, mesolates, all of these other funny chemical things? To make sure the actual drug itself can be absorbed, won't be degraded, will actually be able to be formulated into a tablet or a capsule, whatever it is. For whatever practical purpose, your therapeutic agent needs to be made part of a more complicated molecule so that it can get to where it needs to go. Are you with me on that? So in the end, does the other junk that it's combined with matter pharmacologically? No. You just need to be able to get it to where it needs to go, and what's going to produce the effect is the active drug moiety. So make sure you understand that term. Active drug moiety is the fraction of a molecule that produces the therapeutic effect. All right? And it has a weight. Remember, look at all of those different formulas you can see from the empiric formulas. All the different drugs have different molecular weights. But not only do they have different molecular weights from each other, but the active agent itself, the moiety, might need to be formulated within a larger compound so it can be absorbed. Will that compound have its own weight by the time you add the hydrochloride or the mesylate or the succinate on it? Absolutely. You can kind of see, look at the differences between the compound and the moiety. Let me ask you this before we go on. Which weight is heavier, the compound or the moiety? The compound is heavier because it contains the moiety plus junk, whatever it is, all right? So the other parts of the chemicals that are needed. The moiety is smaller. It's the fraction, the part of that larger compound that includes other stuff that needs to be there. That other stuff will add to the weight, all right? I'm trying to make sure you're going to see. We're just going to be setting up proportional weights. And the reason that's important, let me ask you this. Metoprolol, it's a drug, a beta blocker, 50 milligrams. Is the weight, if that's a dose. Is that the amount of metoprolol, or is it the weight of the metoprolol tartrate? And is that number going to be different if it's metoprolol succinate? See what I'm saying? The weights, the numbers, the capsules, the tablets you fill, the prescriptions you type, is that number representing just the active ingredient, which may be interesting to know. That's how much drug has to be there at the biologic site, but that may not be the weight of the drug in the tablet. The tablet itself may have 50 milligrams of metoprolol tartrate in it. So being able to go back and forth and understanding how the drug is dosed. Is it by the active agent or is it by the compound? Let me ask you this. Following up with this example, iron supplements. Do you guys sell iron supplements? People get iron, right? Especially, pregnant women, people that, have low blood iron. 325 milligram tablets of iron, ferrous sulfate. How much elemental iron is in there? Would it be important to know how much elemental iron is in a ferrous sulfate so that you get the right amount? That's just an example, and I just follow up with this first example here of why you might need to go from the weight of the compound, in that case, the ferrous sulfate, to the weight of just the amount of elemental iron in there. So let's follow up with this example. It says ferrous sulfate syrup contains 40 grams of ferrous sulfate. And again, I give you the molecular weight there, and you can tell it's the ferrous sulfate plus a heptahydrate per 1,000 milliliters. So 40 grams of the ferrous sulfate per 1,000 milliliters. How many milligrams of just iron, elemental iron with its molecular weight, are represented in the usual dose of 10 milliliters of this syrup? So we've got a lot of things going on. We've got the concentration of the syrup. We got the dose we're going to give, which is 10 milliliters. And then we have the relative differences in the molecular weight between the ferrous sulfate and the iron. Okay, where do we start? With all of these, I'm telling you this, you'll mess it up by putting what's the moiety and what's the compound. There's no more important place to start than with every one of these questions, making sure, because the chemical names can get confusing. Define for yourself what is the moiety, what's the active part versus what is it contained in, what is the larger molecule. In this case, the moiety is the iron, the elemental iron. It's contained in a compound being the ferrous sulfate. All right, moiety, iron, compound, ferrous sulfate. You'll see why that's really, really important here in a minute. Okay? Now that we've got which one is which, we need to figure out how much we have of something. So in this question, we can figure the fact that it's based off of the ferrous sulfate. Let's go ahead and calculate the amount of compound. What we want to know is, in this amount of compound, how much iron it contains. So how much are we going to start with? Well, it told us to start with 10 milliliters of this syrup. We know the concentration of the syrup, we said, were 40, and make sure you realize 40 grams of ferrous sulfate per 1,000 milliliters, so that's where that concentration comes from. And again, we're starting with the 10 milliliters. I want to make sure you see where all that comes from. 10 milliliters of a syrup. That's got 40 grams of ferrous sulfate per 1,000 milliliters. And then all I did was convert grams to milligrams so that I could know the milligrams of ferrous sulfate. So would you agree, 10 milliliters of this syrup provides 400 milligrams of ferrous sulfate? Now wait a minute. Ferrous sulfate, was that the moiety or the compound? The compound. We have 400 milligrams of the compound. Because to answer this question, they all, in the end up set it up the same way. So here's I'm telling you to answer these questions, always use the moiety over the compound. Use the small thing over the big thing, okay? You could, it's not a law, you won't break the law, you can do this either way, but I wanted to teach you, if you're going to learn how to do this, to be consistent and to not make mistakes when you set up these proportions, do the moiety over the compound. And what you're going to proportion is use the molecular weights. So we're going to use the molecular weight of the which one on top? The moiety, over the molecular weight of the what? The compound on the bottom. That will proportion. Moiety over compound equals, remember, what did we say this was the dose of which one of those two, the moiety or the compound? The compound, so that you can set it as equal to X over 400 milligrams. You've got to make sure that if you always have the molecular weights of the moiety over the compound, set it equal to, then make sure you get the right weight in the right place. In this case, our dose was 400 milligrams of the compound. So now when I solve for X, I will be getting, the answer is 80.6, and that's milligrams of iron. The moiety, okay? Not hard, right? Not hard. Let's get into another routine. Let's do another question that works very much the same. So let's see if you could set this one up. It says, how many grams of epinephrine bitartrate at that molecular weight should be used in preparing 500 milliliters of an ophthalmic solution containing the equivalent of 2% weight per volume of just epinephrine? So that 2%, that weight, is pure epinephrine. It's not the salt, it's just epinephrine. So I need to know how much of this epinephrine bitartrate I'd have to weigh out to provide that amount of epinephrine. So before you do any math, remind yourself, what's the moiety and what's the compound? Epinephrine is the moiety. It's the active part contained in the compound of the epinephrine bitartrate. All right? Now that we know that, what do we know to start with? We know something about the moiety, because we're told that we have 500 milliliters of a 2% weight per volume of epinephrine. That's the moiety, epinephrine. So let's use that to calculate the amount of epinephrine I would need to make that. If I need 500 milliliters times 2%, which means 2 grams per 100 mils, then again, milliliters cancel, and remember, it's grams of E, of epinephrine, which is the moiety. Everyone okay with that? Not too hard here. If I need 500 mils of a 2%, 500 mils times 2 grams over 100 mils gives me 10 grams. And again, that was epinephrine. That is my moiety. Because now what I can do is always set up moiety over compound. So remember we said the molecular weight of the moiety is that. The molecular weight of the compound, the bitartrate, goes on the bottom. Moiety over compound. Now remember, the amount that I'm trying to replace is of the actual moiety, so that's why it goes on top. So I'm going to set 10 grams of essentially epinephrine, the moiety, over X. Now when I solve it, this proportion will show me a proportional amount of the epinephrine bitartrate that would provide the 10 grams. So you solve for X, and you get 18.2. Does it make sense that 18.2, is that greater than 10? Right? Does it make sense that the bitartrate would weigh more? Why? Because it's the salt, right? It's the epinephrine plus other stuff. The compounds weigh more than the moieties. Going back to this one, because I won't go any further for today, I appreciate your stuff. Does it make sense here that this value was smaller than that value? Why? Because the iron is the small part contained within the iron sulfate. So if you can really start to understand that, then these questions get easier. Now I will tell you, This problem says 500 grams of an effervescent sodium phosphate, so that's kind of a product, effervescent sodium phosphate. I even showed you a picture of the bottle there. So that commercial product, it turns out, contains 100 grams of the active ingredient, which is the anhydrous dibasic sodium phosphate, and the formula there is Na2HPO4 and its molecular weight. So in this commercial product, it has 100 grams of this active ingredient in 500 grams of the product. So it has kind of a concentration there. The question asks, though, how many grams of dibasic sodium phosphate heptahydrate? And the big deal for that is just realize that it's the version, a compound that has 7 water molecules with it. How much of that product do you have to use to basically represent in each 10-gram dose of the actual commercial product? So if you have 10 grams of the commercial product, how many grams of this compound would you have to have in there? So the only trick with this one is you got 3 things. You got the commercial product, you've got what is the active ingredient in there, what's the active thing doing something, and then what is the compound used to provide that active moiety. So I would tell you with all of these questions is write those out. Before you try to do any math, make sure you know what's what. So in this question, I'll remind you the commercial product is the effervescent sodium phosphate. But the active moiety within that product is the anhydrous sodium phosphate. Now don't worry about the dibasic, it's all dibasic, we'll just ignore that. The moiety is the anhydrous sodium phosphate, and that's going to be provided for the compound in the form, or the product in the form of a compound, which is the sodium phosphate heptahydrate. So I give you some abbreviations there so we can keep track of that. All right, so we got our 3 things. We've got our product, our active moiety, and our compound. Where do we start? Well, we're going to start with the commercial product because we're starting with, we want to know how much is in 10 grams dose of that commercial product. So let's start with 10 grams of the ESP, or the effervescent sodium phosphate. I've got 10 grams of that. I was given a concentration of that. I was told how much active ingredient, in that sense of anhydrous sodium phosphate, was in 500 grams of that. I know there's 100 grams of my active moiety in 500 grams of product. So if I set it up that way, then I can multiply by 100 grams of the active product, or the moiety ASP, in 500 grams of the effervescent product, then grams of ESP cancel, and I determine the total weight. So in my 10-gram dose, it turns out 2 of those grams is actually what contains the active moiety. Okay, so now the question is, how much of the compound do you have to provide that much active moiety? Let me ask you now, will it be more than 2 grams or less than 2 grams? Do you think the moiety, does the compound weigh more or less than the moiety? Weighs more, right? There's more stuff to it. Now, it's not active stuff, but it's more stuff. So I guarantee you in the end, the weight of the compound we're going to need is going to be more than 2 grams, because in the end, it's the amount that provides us 2 grams of active moiety. So how do you find that out? It's pretty straightforward, right? Remember, we always said set up a ratio of your molecular weights and always get in the habit of putting the moiety over the compound. So we were given the molecular weight of the moiety at 142 for just the sodium phosphate, or the anhydrous, and we'll set that over the molecular weight of the compound, or the heptahydrate, which we were given at 268. You set a proportion of the molecular weights. We can set that equal to, now which weight did we have? We had the weight of the moiety. So we're going to put the 2 grams on top. That represents the weight of the moiety, and I put X on the bottom. Then when I solve for X, I'm solving for the weight of the compound. So if you solve for X, you get 3.78 grams of the heptahydrate. That's the weight of the compound. That would provide you essentially 2 grams of just the active moiety. Okay? Any questions on that? Once again, you guys are the ones willing to sit here. If you got questions or something, please holler at me. All right. This is a little more difficult because it's a kind of a variation. We're going to solve it the same way with the proportion here, but it's kind of a different question. So let's make sure you understand what's different about this. It says, the formula for Albright's solution M calls for 8.84 grams of anhydrous sodium carbonate, and that formula is Na2CO3, okay, per 1,000 milliliters. So we've got a formula that involves sodium, anhydrous sodium carbonate. However, we want to know how many grams of a 95% weight per weight sodium hydroxide powder, and it's still a powder, so we've got this sodium hydroxide powder, to use instead of the sodium carbonate. All right? And in the end, we want to know how much so that we can make a total of 5 liters of this solution. So I want to make 5 liters of this solution, but instead of using the sodium carbonate, I want to use the sodium hydroxide. All right? So it's not an active moiety within a compound, it's 2 different compounds. So the first thing we want to do is let's write those out so we can be consistent with our proportions here. What I just, and again, this is super important, but I said compound 1 is what was called for in the original formula, which was the anhydrous sodium carbonate. I'm going to call that compound 1. Compound 2 is the sodium hydroxide. And again, the formulas are very important there, so I listed out the formulas as well. Because here's the deal. What are we trying to replace? I mean, what is the same thing in sodium carbonate that's the same thing in sodium hydroxide? The only reason I could replace one with the other is that the sodium hydroxide replaces what? Sodium. So clearly we want to be able to put an equal amount of sodium. We want whatever sodium would have been there with the sodium carbonate, we want to replace with the sodium hydroxide. All right? So let's make sure we set up, though, what is equivalent. So if we put compound 1 over compound 2, sodium carbonate over sodium hydroxide, you got to look at the formula. And the formula is sodium carbonate is Na2CO3 on top over NaOH. All right? So let me ask you, if we're trying to replace the same number of sodium molecules, if I have one molecule of sodium carbonate, how many molecules of sodium hydroxide do I have to have? 2. That's the idea behind this. And you're going to see that we're going to have to use that 2 when we set up our molecular weight equivalents, okay? It will take 2 sodium hydroxide molecules to replace the amount of sodium from 1 sodium carbonate. Okay? You'll see where we're going to take that into account here in a minute, but it's very important that you understand that relationship and that the molecular formula is what the basis of that is. We want to give the same amount of sodium, so we have to look at the formulas and account for that. All right, let's step back though. Let's figure out how much we need. If we were going to use sodium carbonate, how much sodium carbonate would we need? So we're trying to produce 5 liters, so let's start with 5,000 milliliters. That's the volume we're trying to prepare. And we have a formula. The formula said to use 8.84 grams per liter, essentially. So I'm going to multiply that times 8.84 grams of sodium carbonate over 1,000 milliliters. My milliliters cancel, and again, that would tell me that I need 44.2 grams of sodium carbonate. All right? So far so good. That was the easy part. So now all I need to do is let's convert from the weight of sodium carbonate to an equivalent weight of sodium hydroxide. We can do that by setting up our proportions of the molecular weights again. So remember, I'm going to put compound 1 over compound 2. So I put the molecular weight of sodium carbonate, which is 106 on top, and I put the formula weight of the sodium hydroxide on the bottom, which is 40. This is what I'm saying here. Can 1 sodium hydroxide replace the same amount of sodium as 1 sodium carbonate? No. How many do I have to have? 2. What is the molecular weight of 2 sodium hydroxides? 80. Does that make sense? So that's why there's the times 2 down there for the 40. So it's 106 on top, because I only need 1 sodium carbonate, but on the bottom, to have an equivalent amount of sodium hydroxide, I have to take 2 sodium hydroxides. So since the molecular weight is 40, I'm going to have 40 times 2. Okay? Once I set that up, I've got compound 1 over compound 2. I'll set that equal to, remember, we've determined the weight of the sodium carbonate. The 44.2 was sodium carbonate, so 44.2 grams of sodium carbonate over X. Solve for X, and you get the equivalent weight of sodium hydroxide. So this is the amount of sodium hydroxide that is equivalent to that amount of sodium carbonate. And that's what I needed to know. But that's pure sodium hydroxide. What was a little bit of a last wrinkle in this question was the sodium hydroxide we're using is not pure sodium hydroxide, it's what percent? 95%. So the last step is say, okay, if that's the amount of sodium hydroxide I need here, then let me just multiply it by its weight percent. So it was 95% weight per weight, meaning 95 grams of sodium hydroxide per 100 grams of this powder. So 100 grams of powder on top, 95 grams of sodium hydroxide on the bottom, so that those cancel. And in the end, this is the amount of the powder I would need to weigh out, because the 35.2 grams is only 95% pure, so that's why it only provides 33.4 grams, which is the equivalent amount of sodium chloride that gives, sodium hydroxide, that gives the same amount of what we need for sodium carbonate. Okay? Any questions about that? It's a little bit different than the active drug moiety and compound, but it's the same thing. And this was the basis, I don't know if anyone remembers, but when I went through kind of the exam, we talked about with that sodium acetate question at the very end, I showed you how you could use a weight proportion as well to do it. And it's kind of the same principle as what we just did here, where you can do compound 1 and compound 2. All right, and there's not too much to do left with this lecture. I thought this would be kind of interesting, though, because it does talk about active drugs. Almost all of your commercial products out there have an active moiety along with some salt. And I'll remind you, why do they make it with some sort of salt or something? For absorption or solubility or stability, some reason they have to mix it with something else to be stable in a form. So the one that always came to my mind was diclofenac. I don't know if you've ever heard of diclofenac. It's a non-steroidal anti-inflammatory. They use it for arthritis and pain relief. But I know it comes in different commercial dosage forms. And again, what you can see listed here is the same active ingredient diclofenac in 3 different commercial products. So if I use the brand names, it's Cataflam was the brand name of diclofenac potassium, which is the tablet you just swallowed to get it into your body and to have it produce its effect that way. But they also reformulated it as a topical gel. What I thought was kind of interesting, and to be honest with you, I don't know exactly why, but when they formulated it to be topical, to be absorbed through the skin, it worked out, instead of being the potassium, for whatever reason, they made it as diclofenac sodium. Okay, there you go, it's just a different salt. But then they've recently come out with it as a patch. So they'll put a patch on, the same active ingredient though, but they've mixed it with a salt called epolamine. And I'm not even sure what that is. It's not very common salt to be used, but diclofenac epolamine, for some ever reason, works better when you have to formulate this in a patch. So my question to you is, if you look through all of those different dosage forms, they have different strengths. Now I'm going to ask you, which one of those provides the most active moiety per day? Given the maximum dosing that's kind of listed there, those different dosage forms, they're all the same drug, which one of them actually provides the most amount of diclofenac, active moiety on a daily basis? Could you figure that out, even though they're all different salts? And each different dosage form has a different amount of that salt. So let's do that. I think you can do it. So if we start with the Cataflam, I told you that the maximum daily dose is 1 tablet every 8 hours. So that's every 8 hours, 24 divided by 8, that's 3. So 3 times a day. So let's take 50 milligrams times 3 tablets per day. The total amount of the diclofenac potassium is 150 milligrams per day. Well, we can figure out how much just diclofenac is in there by setting up our proportions of moiety over compounds. So we'll put the molecular weight I gave you for diclofenac at 295.13 on top. And for the diclofenac potassium, I gave you the compound weight at 334.25. You set up that proportion, set that equal to X on top, which is the moiety, over the weight of the compound per day, which is 150. So let's just solve for X. So you come up with that, you get 132 milligrams. So on a daily basis of just the active moiety, you'd get 132 milligrams. Do you think the gel is going to provide more or less than that amount per day? Well, let's find out. Same way. The only trick is, this is kind of interesting. I told you the maximum weight of that gel you can apply, whether it's on the arms, the elbows, the knees, wherever you're going to need to put it, is 32 grams per day. So if you're going to use a total weight of 32 grams, keep in mind the gel itself is only 1%. So how much of the diclofenac sodium is in that? Well, 32 grams times 1 gram of diclofenac sodium per 100 grams of gel. That cancels out, and you can get a weight there. And then we got to convert. I converted that weight. So again, this converts grams here. And now I'm going to get rid of grams to milligrams. So if you multiply that all the way across, you get 320 milligrams of diclofenac sodium. How much diclofenac moiety is in that? Well, set up the same proportions, but now you'll notice the compound, we have to use a different compound weight because diclofenac sodium has a molecular weight of only 318.13. Set that equal to X over 320, which is, again, the weight of the compound on the bottom is the 320. Solve for X, which is the weight of the moiety, and it's 297. Would you realize that you're getting more than twice or almost twice as amount of drug using the gel, if you used it at that amount, as you would from the tablet? Okay? Last one, because it's the same sort of thing. What do you think from the patch? So the patch is dosed twice a day, and there's 180 milligrams. And we are assuming all 180 milligrams comes out, which isn't always the case. But if we say 180 milligrams times twice a day, that's 360 milligrams per day of the compound, which is the diclofenac epolamine. But how much diclofenac is in that? We'll set up the proportions, weights of moiety over compound, X over 360, and you get 258. So in the end, which one actually provided you the most, at least exposed or dosed most per day, would be the gel, followed up by the patch, and last the tablets. Can anyone tell me why you might get more or that they would dose a higher amount on a skin or a patch than they might do on a tablet? It has to do with our next lecture on pharmacokinetics. bioequivalence or bioavailability. Turns out you're not going to absorb as much through the skin, so you might have to put more on the skin to get the same amount that you can actually absorb into the blood from the tablet. So a little preview for our next lecture here a little bit. But in the end, it was kind of remind you that different commercial dosage forms of the same active moiety like Diclofenac have different products. All right, last question on this lecture. I like this one because it ties in both parts. I'll remind you the very first thing we talked about was adjusting formulas, which was pretty straightforward, but we've got to make sure you can do that, and this will also carry over into our active drug moiety. So it says, we have a formula, and this is a combination of glycolic acid and lactic acid, and I show you a picture of actually a commercial bottle. This is used as an exfoliant. It kind of basically helps rub off, if you will, or slough off the top layer of skin, so it'll help kind of get to the newer skin underneath there. So we have essentially a formula that calls for 5 grams of glycolic acid, 5 grams of lactic acid, 2 grams citric acid, 2 grams tartaric acid. A certain amount of acetyl acid alcohol, which is kind of the emulsifier that gives it some stiffness or thickness to it, and then some water to disperse it to a total volume of 100 milliliters. So we have that formula. And if we follow that formula exactly, what volume of our final product would we have? We'd have a 100 ml bottle, right? But are we always going to want a 100 ml bottle? No. So in this question, if you actually read the question, it says, using this formula, tell me how much you need for each ingredient if you're going to make 8 60 milliliter bottles. So if you're going to make a larger batch, please reformulate that formula so that I know how much to use in my batch, which is going to be for 8 60 ml bottles. All right? Easy enough? Where do we start with that? Well, I need to know an exact volume. 8 60 ml bottles doesn't help me. How much does that really mean? So let's figure out. I got 8 bottles times 60 milliliters per bottle. That really means I need 480 milliliters of this compound total. So I need 480 mils. So are we making more or less than the original formula? More. So we need to scale everything up. Remember how to do this? It was to create a conversion factor. I even made you say this in class last time. Something about actual or recipe versus desired, which was which? It's desired over standard, remember? So we're going to put the desired amount over the standard amount. So the desired amount in this case was 480 milliliters over the standard amount in the formula, which was 100 milliliters. Units cancel, and we get a conversion factor, or an adjustment factor in this case. So the adjustment factor is 4.8. 480 divided by 100 is 4.8. We need 4.8 times the amount of each ingredient specified in the recipe. Easy breezy. Hopefully this is easy. What did I warn you about, though? So you're going to go through, and what I told you to do is line up each ingredient with the amount called for in the original prescription, multiply it by the adjustment factor, and there are 2 things I warned you about. Be careful with your units. Remember, the conversion factor doesn't change grams to mils or mils to grams, so in this case, you're going to keep your units across as you multiply. So for the first couple of ingredients, glycolic acid and lactic acid both called for 5 originally, so 5 times 4.8 gives you 24 grams for each of those ingredients. Citric acid and tartaric acid needed 2 grams originally, times 4.8 gives you 9.6 grams of each of those. The acetyl alcohol was 60 grams, so times 4.8, that increases it to 288 grams. And then lastly, we're going to add 480 mils of water, correct? Well, a couple of things. No, well, be careful. It's 480 milliliters. The units are still milliliters, but don't forget the QSAD. It basically is saying you're going to have up to a total of 480 milliliters. So remember, when you use your adjustment factor, don't change the proportions within the prescription. Make sure you keep units, grams are grams, mils are mils, but don't forget to keep everything in the right proportion. So it would be to a total of 480 mils. Okay? That's easy. But that's the way you do it. Let's see, this could be a little more difficult for some of you because, let's go on, it says the lactic acid that we want to use in this product is only available as an 88% weight per weight solution with a specific gravity of 1.21. How many milliliters of the lactic acid do you need to prepare the 8 60 ml bottle? So given our revised version of our amounts for all of that, how much lactic acid solution from this bottle do we need to actually have to use? All right? So I'll remind you, there's the formulas. We did that. So our revised amount of lactic acid for our larger batch is 24 grams. So what we're trying to say is I need 24 grams to make this batch. Well, if I'm using an 88% weight per weight concentration, that means 88 grams of lactic acid per 100 grams of lactic acid solution. So that's my abbreviation. So I set it up like this. So again, the lactic acid is on the denominator, 88 grams of lactic acid. under 100 grams of lactic acid solution, because what I need is 24 grams of lactic acid. If I do that, I now have the weight of this solution. Am I going to measure a solution by weight usually? No, so let's convert the weight of that solution to its volume. We can use the specific gravity for that. So we were given that as 1.21. That one means 1.21 grams per milliliter. So I set it up like this so that grams cancel. So that's why I set it up like that. If you do that math all the way across, you get 22.5 milliliters. And I do have a volume that essentially provides the weight that I need, the 24 grams. Kind of a review, hopefully, in terms of that math, I hope. All right, so part 3 is really the last tie into our active drug moiety idea, because it says you have on hand citric acid monohydrate, okay? That's the monohydrate, it has a water molecule in it. But the prescription calls for actually, if you look at the ingredient in the prescription, it's actually for the anhydrous citric acid. So essentially, how many grams of the monohydrate will I have to use to provide the amount I need of the anhydrous citric acid? Okay, so the prescription called for anhydrous, and again, how much did it call for? I'm just trying to back up because I didn't do that again. If you look over here, the revised version is 9.6 grams. So I need 9.6 grams of the anhydrous, and yet I need to know how much of the monohydrate to provide that. So let's again write out which one is which. The moiety is the anhydrous, and the compound is the monohydrate, the one with the water. So moiety and then compound. Let's set up a ratio of our molecular weights, and I was told that the anhydrous is 192.12, whereas the monohydrate was 210.14, so I set up that proportion of moiety over compound. And remember, I calculated that I need 9.6 grams of the moiety, that's what was called for in the prescription. Set that over X, solve for X, and I see that I need 10.5 grams of the monohydrate to provide the amount of the anhydrous that I need for my formulation. So hopefully we're able to get to the 10.5. Questions on that? That was kind of the big important thing. We always have to end a lecture on something like arsenic, just because it's kind of cool and weird. So let's read the last question there, because it says this. It turns out that this monohydrate that we're using has potentially a little bit of arsenic contamination in there, but we're assured by the manufacturer that it's not more than 3 ppm. So this is just reminding you, what the hell does ppm stand for? Parts per million. That's a big number, but you stay calm. That's not going to throw us off. So it could have as much as 3 parts per million by weight. Therefore, what is the maximum amount of arsenic that could end up in our final product? Well, if it's only coming from the citric acid monohydrate, we just calculated that we're starting with 10.5 grams of that. So let's start with the 10.5 grams of our citric acid monohydrate. We were told its concentration is 3 ppm, which you guys are now good at saying. That means 3 grams per 1 million grams of compound, because it was told it was 3 ppm by weight. Units for that, parts per million, are going to be grams per gram. So 3 grams of arsenic per 1 million grams of our citric acid powder, okay, monohydrate. Set it up that way so that my units cancel. And again, I don't have to do my math quite yet because I'm in grams, and the question wanted milligrams. So, or micrograms, I should say, wanted micrograms. And you can do that all in one conversion, but I go from grams to milligrams by multiplying by 1,000, and then I went from milligrams to micrograms by multiplying again by 1,000. So if you do that math all the way over, you end up with 31.5 micrograms. The maximum amount of arsenic you might get from that. So hopefully those last couple of questions were a little bit of a review. Any questions or issues or concerns with that?